for Inventor users as an add-in to Inventor, and hopefully I will be able to best illustrate to you in this webinar how visualization is done in EMS for Inventor. So I'm going to make Ahmed the presenter now. There we go, Ahmed.
Good afternoon, everybody. Welcome to this series of webinars of EMWorks. And today I will show you the, usually we go through all the steps, but now it's a more specialized webinar to show you more in details how to visualize your results in EMS Inventor. And again, as many of you know, that the EMS is an add-in to Inventor, and it is actually the only electromagnetic add-in to Inventor. So I'm not going to go through all the steps, how to create study, and nevertheless, if anybody has a question about the pre-processing, I would be glad to answer it. So once you, after you run your analysis, the feature manager tree changes, and now you're going to have many different folders representing different results. So the first type of results are the tabulated results, or the lumped quantities. These quantities are that you cannot, they're not distributed quantity like a field, and then you cannot present them on mesh. So one of them is energy, so you can look at stored magnetic energy. And by the way, I'm showing you the AC magnetic of three-phase transformer. The flux linkage, and notice that you have 6 coils, and in each coil you're going to have separate flux linkage. And flux linkage is directly related to inductance. Okay. Then have the current. So this particular example, you have 3 primary coils and 3 secondary coils. So the secondary coils, they don't have, we don't apply any current or voltage in them. So whatever you see there in the coil itself is really the induced voltage in that particular coil. Voltage, actually this is the current, this is the voltage, okay? That's the voltage. Okay, yeah, so it's, these are basically the induced voltages in secondary and primary coils as well. Then you have the inductance. Well, the inductance is a matrix, because if you have 2 conductors, you can have the self inductance and mutual inductance. As you notice here, that the self terms are always positive, and the mutual terms are negative. Okay. And the mutual terms are generally smaller than the self term, and as you go away from the diagonal, the mutual terms tend to become smaller and smaller. Okay. Along with the inductance, you also have the impedance. Okay. So again, the impedance is a matrix, and you have a 6 coil in this case. Doesn't matter what current you apply or voltage. You know, the impedance or the inductance doesn't depend on the current or voltage. It really depends on the shape and the excitation. I mean, the shape of the coil and the number of turns. So this is the inductance matrix again. Coupling coefficient, while this is useful, what it tells you here, like say coil 1 and coil 2, tells you, okay, if I take the coil 1 and coil 2, earlier as you can see the self terms are always 1, right? So if I take coil 1 and coil 2, so I know between coil 1 and coil 2 there's a coupling coefficient of 0.427. So what does it mean, coupling coefficient? Which means the amount of energy transferred between coil 1 and coil 2 through the magnetic circuit, and so on and so forth. So these are the coupling coefficients for H2 winding or coils. Losses, okay, in AC magnetic or time harmonic, you're going to have, in addition to the ohmic loss, you're going to have eddy losses. And in this case, hysteresis, you could have it also, but in this particular case, you don't have any of excess loss, and the sum of the eddy hysteresis and excess loss is called core loss. So that's how much core loss you have. As you can see, most of this part, they have ohmic loss or joule losses. And of course, the air part, they don't have any losses. So it's very general in terms of giving the breakdown of different losses versus giving just the core loss. So now you could export all the results, and you have different formats here. So whether CSV file, text file, or a Microsoft Excel sheet. So that's then you can do further post-processing with it in other programs or in lab or so on and so forth. Okay. Once you're done with the results table, you can close it, and of course you can always reopen it. Okay. All right. Now being a field solver, EMS solves directly for the Maxwell's equations. And the variable or the unknown actually solves for is really the magnetic field. So all of the results table data is really a post-processing. So we solve the Maxwell's equation directly, obtain the magnetic field in all at each node in the finite element mesh node. Okay, and then from that we derive everything, whether it is the energy, inductance, capacitance, force, torque, flux linkage, impedance, voltage, current. All of them are actually derived from the the field data. Now, it is therefore important to be able to visualize and look at your magnetic flux density, how it changes. Because if you want to improve your design to get a better coupling, less loss, more torque, less force, whatever your design goal is really to, you have no other option but to go down to the basic physics or the field, the field data. You have to understand it, you have to plot it, you have to dissect it, bisect it, and look at it and see where you may have this. You may have saturation in some points, so you can locate the hot spots. So let's start by magnetic flux density. So you right click, you have 3D and 2D plot. So let's start with 3D plot. All right. Now in 3D plot, you can plot any component, the XYZ component of your magnetic flux density. You could select units, Tesla or Gauss, and you can have fringe or vector. Under the fringe, you have continuous, discrete lines and points. So let's demonstrate the continuous. All right, so I say, okay, the magnitude. I'm going to say, okay. All right. So that is my continuous fringe plot. Tells me about the main and max overall in the overall structure, but I'm going to need to know where is the mean, where is the max, and whether I'm saturating the steel. Definitely here I'm not saturating, we're not saturating any steel. The flux density is very small. So how to do that? Well, there are different ways to do that in EMS. One way is to do a section clipping. So now you want to cut your model at any of the three planes. Okay? You could do inside out, or the other way around, or you can plot on section only. Okay? So by the way, as you can see here, because we have an AC, we have eddy current, we have skin effect, and all of the field, most of the field is on the skin, and inside is very small because it is an eddy current type of solution. If you do magnetostatic or static, really you don't see this behavior. The other way around, the field will be higher at the center of the core instead of being right on the skin. Okay, so this is the my section plot. I can move my section. I can tilt it around various axes. Okay. I can add another section, and there are some options over here where you can, if you want to see it overlaid with the mesh, you can also look at the mesh to see, make sure that you have a nice mesh there. So you can hide the wireframe. The model origin you can hide all of this. Okay, if you see just the plot itself without the wireframe, or you could have add a second section. Okay, and let's be now in different planes. Okay. And the third, and the fourth, and the fifth, up to 6 section, or superimposed. You could, do various kind of sections where you can see, how the values, the flux density changes from one position to another using section. And you can always zoom in if you want to zoom in with the wheel of your mouse, just in and out. Okay. Okay, so that's the section plotting. Now let me generate another one, but this time instead of continuous, I could put points. Okay. Well, that's points type instead of the continuous, and I can do exactly the same thing again with the section clipping. Or this time around, I want to do ISO clipping. So the ISO clipping is going to allow me to actually look inside the model and see where my maximum is and where my minimum. So say inside, and now I could move my cursor. Okay. What's happening here? I think probably the point, the point probably is not optimized with the clipping. So let me go back to the fringe and do ISO clipping. Now I should be able to, all right, there you go. So what do I need this? Well, you want to know where the maximum is, right? A lot of time you want to know where you are saturating the steel, where we have too much losses, joule losses or eddy losses, and you want to locate it exactly where it is, where in the model, so you can walk around and improve your flux. And by improving your flux density or magnetic field, you are eventually improving the tabulated or the design parameters like flux and flux linkage and inductance, impedance, forces, and torques. I could do the other way around. If I want to see the minimum, I leave only the minimum, so I could go and go. There you go. Okay. All right. Now, let's look at maybe now at the do some maybe another feature on the magnetic flux, on the magnetic field itself. So I could do now the vector plot. While the vector plot, they're going to give me the line of field, so I know how my field is circulating in the magnetic circuit. So there you go. In this case, you know, it's mostly in the air gap. So actually, the vector plot is actually nicer with the magnetic flux density, because it's really inside the core instead of because the magnetic field is really higher in the air gaps, and the other way the magnetic flux density is the other way around, is higher in the magnetic material, and we know that B loves magnetic material. All right, so this is my vector plot. Well, there are different things you can do now on this vector plot. You could, there are vector plot options, and if it is too long, the arrows, you can make them smaller, and it's too cumbersome, you can make the density less dense. I have 2D shape or 3D shape. And you can see, I can go back to my 2D shape, and a different, can fill it. You could have vertex, you could have dashes, all kind of options, different arrows. So now sometimes it's you know, in the model you cannot really see. It's a vector plot. What happens if you want to really look at one particular component, and you could use the isolate. So I can isolate one particular part. Suppose I want to isolate, say, this particular coil, inner coil 1. Then I'm going to say isolate. Okay, now go back to my EMS feature manager tree. I want to look at the, say, applied current density. Okay, how much current I applied. And there you go. So if you know, you could do that also by hiding a certain parts and hide and show, but I prefer personally the isolate. Okay? And then the vector plot itself, and as you can see now, the current is flowing in the right direction. This is current. This is the applied current density. So it's how much current we applied in coil number 1, primary coil number 1. Now, we could also do the section clipping in the vector plot as well, you know. And sometimes you want to see in one particular plane how, while this no-brainer in this particular case here, the current is flowing around in the coil, but in some situation you want to see one particular plane, how does the your quantity, the flux or field, or okay, circulate. So I can move it in and out. And again, the same thing, I can tilt it, okay, around various axes. Okay. Another type of plot is, now I can go back to my model, and I'm going to say undo isolate. So I can go back to my original to be able to see everything. Suppose I want to see now the eddy current. Okay. So the winding, because we usually there are thin conductors, insulated, so there's not much eddy current, but most of the eddy current will be in the core. Well, it's a vector in this case, and as you can see, the eddy current flows in the opposite direction of the applied current. Probably I could do a fringe, but this time I'm going to do lines. Okay, and then I can do again a section clipping, and I can plot on section only, and then I can move. I can also change the density of the contour lines. Okay, the same thing, you can have up to 6 sections or superimposed. Okay, so in the AC magnetic or time harmonic magnetic, we have all of these quantities. So you can look at your magnetic flux density, your magnetic field, applied current, and current density. Now, there's a difference between applied current and current density. Applied current is how much current you apply in the winding. The current density is sum of two, so it's in the winding, it's both, but in the core, it's really the eddy current that generated in the core, and that's very important, especially for one motor transformer. Almost, you know, the skin effect or eddy currents are very important to account for in a new design. There's force density because we cannot force is really a lumped quantity. It's not, you can say the force on a component. We cannot say the force distribution really on each different node. We can talk about force density, yes. This is my force density, okay? And that's Newton per meter cubic. It's different from force. So at each node they're going to have a force density, but it's different from force. This is the force density is an indication about how much stress and deformation you can induce in your steel or other parts. You can also look at the electric field. Losses, you can plot all type of losses 3D. So I can plot ohmic loss, eddy, hysteresis, excess loss, and core loss. Let's say I'm going to plot the core loss in this particular case. Okay. Okay, it's loading the data. Right, it's now, okay, now the temperature also, so in addition to the field data, the magnetic electric field currents, losses, you also can plot the temperature distribution due to current losses, be it in the winding or in the core. So in the winding you're going to have, well, both in the winding and the core, but you're going to have many losses actually. You're going to have the ohmic loss, the eddy loss, and what's called the core loss general. And that generates heat. Oftentimes you want to know how much heat you're generating, whether you're going to you know, whether you want to find ways to cool it or to there are certain UL or whatever regulations. Sometimes you have to certify your component instead of transforming, instead of making it and measuring the temperature. You can actually simulate it and get a very accurate temperature. Okay, so this temperature is due to the losses. Okay, so all I've done with well, except now for temperature, I don't have vector, okay, because temperature is a scalar quantity. However, the temperature gradient and heat flux are so they're vector quantities. Now, I have the chart options. Now, in the chart option, I can show min and max. I can hide the plot data details. I can hide the color chart. And I can change the scale. So by default, it's going to show the min and max range on shown parts only. I can automatic or can define it. So if I'm not interested to know what's happening between 26 and 61, I only may be interested to know what's happening between 60 and 61. I can type 60 there and 61. Okay, there you go. So anything outside that range, I don't see, I don't care, I don't see. So that I can make it even, you know, tighter, or I can change the range. Yeah. So the min and max or the range can be either automatic or with respect to shown part only. This is very useful if you have only a small part and the data, the temperature or field is very small, and when you plot it in the overall environment, you don't see much change. So you could, in that case, isolate one that particular part, or hide other parts for that matter, and use this shown min max with on shown parts only. Okay. The positioning of the color chart is also flexible, so I can move it. I can move it up or down. Okay. I can use a thick, okay, or thin, and I can change the numbers to scientific or maybe floating. Sometimes you just use the scientific notation. This gives me the title horizontal position and title width, title vertical position. So all of them are, you can customize them and contour them. I could put maybe the color chart on the left side if I wish. There's also the color options. You can have the number of decimals. So if I want to have less, there you go. I can have just one. I can change it. Now, the color map, I could have 13 or probably more. So if you want more colors, you can clearly see the difference between different colors. You can add more or less. Okay. I can flip that. Okay. And this is the default. I can use a rainbow scale or gray scale. So if I don't want the color that's just gray, I can do that as well. Okay, so let's go to the default. So all of these are customizable from the chart options. Okay. Now, and again, I can look at the temperature gradient and heat flux, and notice that while solving this electrothermal problem, there is no need to exit the program and do a thermal solution, because it's all integrated in one environment, in one solver. It's just in this case, just put the convection coefficient in the oil or the air surrounding your transformer in this case. Okay, so all of these quantities you can plot the heat flux and temperature gradient. You can also, so one thing you notice that, sometimes it's not easy to do the mapping between numbers and colors. They're nice for presentations and to give you overall idea, but if you are interested in to really know the exact number, sometimes it's not obvious from the color chart. So we have this nice tool, it's called 2D plot. Now the 2D plot allows you to, let's see if I need 2 points. Okay. So if I want to go from this point, say, this point over here, okay, I divide that segment by 20 points. I can change my temperature, the units in this case, it's a temperature, so, and then you say, okay. Now it's going to plot temperature in the y-axis, as you can see. There you go. Okay. And I can make my curve thicker, thinner. It's my temperature and the distance. So what distance is this? The distance between 0.1 and 0.2. So 0 being 0.1 and 11 is, 12 is being 0.2. So as I move along that segment, I can see, I can track the values and see how it can change. Well, you may say, okay, I have to, at each point I have to see, well, corresponding value. But, well, if you want to see the number, the listing, then there you go. So at each position, you're going to see, in this case, the temperature or any other data or quantity that you can plot on the mesh. You could zoom in, zoom out, print preview. If you want to print it, you can go to back to plot. You can export the data to the regular format, is text file or an Excel sheet. Okay, so let me emphasize, that the importance of the 2D plot. The 2D plot, if you want to know not just color, you want to see numbers, values, the design values. Okay, really, your tool is the best tool is 2D plot. Okay, and it should have many different segments. It doesn't have to be 2 points. If I could also use edit maybe this, and I can keep adding other points. Okay, and then there you go. It's going to update. Now we have more points. So new model, wherever region that is very important to you, you want to have maybe a couple of points and plot your data and export it in whatever format you prefer. Now, there's also the listing. Okay. So what does listing do for you? It's at each mesh node, because this is finite element, by the way, of course. So you're going to give you the coordinate of the point as well as the value. This case happened to be the temperature, but any one of the other data you can plot. You can export it again to different formats. So the temperature gradient also, now the temperature gradient is a vector. Okay. And because it is a vector, you can edit, and you can plot different components. If you are interested in the temperature gradient only along Z, be it, so you can change that. Yeah. And any one of them, I can do the section, the ISO clipping, and 6 sections in each type, either in the ISO clipping or in the section plotting. So what else I have here? Of course, you can save your plot, you can print, you can do all of this. You can rename, if you want to rename your plot, you could definitely do that, okay? So I can say plot 1, okay? You don't have to live with this default naming that we have. Okay, now after you visualize your data and you want to document your work. So the question is how to document that. We automated the report documentation or the documentation. So by defining define a report, what that can give you, all right? So you can customize, personalize your company logo, title, company name, author, company name, you know, and while it's timestamped in today's date. Different sections in the report, you may pick and choose which section to include, so you can select, check, or uncheck various paragraphs or sections. So if I don't want any introduction, I go straight to materials, or if I don't want any other sections, I can unselect them. Now we have give you a choice between an HTML, Microsoft Word. You know, obviously HTML if you want to use on the internet or other, you know, HTML or help or, you know, some other format usually. But if you want to probably share data as a PDF file, maybe you want to do the Microsoft Word file. Now it's going to generate. So you don't need to worry about taking notes, what material you entered, what current you applied, what voltage, you know, because all of that is automatically documented for you through the report. Now it's dumping the data to the Word file, and of course if you have a large model with millions of elements, this could be a little bit slow. All right, where is my report now? Here we go. So it's a regular Word file. You can edit it. Yeah. If you want to go to one particular, you know, you can hold down the control key down and you go straight to a particular plot. So you have the material data, load restraints, call information, results table. All the results are in the file, in the report. All the plots, anything that you plotted is written to the file. And because it is a Word file, then you can generate a PDF file as you wish, if you wish that. So that is basically what you can, these are the various visualization and reporting option in EMS Inventor. One thing I want to say before opening the floor for questions is you can always, you know, if you have, you can always clone your study, okay, and you can copy, drag it, or say, okay, and then I do a copy study, maybe 3 or 4, whatever. Then all the results that or the data that I have in the previous study are saved. Okay. Now this is going to give me a copy of my study, and then I can change whatever parameters, design parameters that I want, whether material, current, or voltage, and run again. And I could also run all studies. Now, it can be a little time consuming if it has a lot of data, but it's definitely much faster than redoing the whole study. So there you go. So you have your study. Okay. And in this study, if I want to, for instance, if I want to plot to the plot, okay, let me see if we can superimpose. No, this one doesn't have compare. Okay, so then you can have a clone of that study, change whatever you want to change, and run again. And you could also, before going home in the evening, run all studies, and when you come in the morning, you should find all the results compared for different studies, when you can pick and choose the what suits your design best. Okay. Okay, so that's it. That's it for the visualization EMS Inventor. If anybody has any question, I'll be glad to answer it.
Please type your questions in the chat box. Type questions here, please. And we'll answer them one by one.
All right, it seems that my presentation is so good, so clear, that nobody has any questions. So with that, I'm going to turn the microphone to Adam. Okay, and thank you very much for your time. And if you don't have a question now, always have a chance to ask your question by sending an email. I will be glad to answer any questions that you may have.
Thank you, Ahmed, for your presentation. So just wanted to type that for any sales-related questions, please address them to sales@emworks.com. As far as technical questions, please address them to support@emworks.com. And we are having another webinar next Tuesday, same time, 2 p.m. You're welcome at 2 p.m. And next Tuesday's webinar is going to tackle the subject of electro-thermal analysis in EMS for Inventor. So, please visit our website, www.emworks.com. Thank you all for your attendance. We appreciate it. And you all have a great afternoon. Bye.